suck. I don't get them when you angry. I'm gonna send angry email myself. I'll be like, yo, what the fuck, man? Period. Can I try again? Honestly, I think like within the 6-month window was like graduation.
Can everybody hear me out there? Okay. So last time we talked about convex hulls. Convex hull of a point set is the smallest convex polygon, or more generally high dimensional polytope, that contains all the points. And it's generally the shape of the point set. Right? So the interior points are eliminated, only have the exterior convex hull points. And it generalizes to arbitrary dimensions, lots of applications, it can be gaming and simulation. And it's a very ubiquitous problem. So we came up with an algorithm, Jarvis's March, named after the guy who invented it back in the early 70s. His name was Jarvis. You basically rotate a line and you keep tracking this supporting line around the periphery of the point set, detecting a new convex hull point at every step. Of course, you don't literally do it continuously as an algorithm. You do it discretely, but you find the point with the best, smallest angle compared to the point that you're at now. And once you keep doing this, you find a convex hull. And this is called sometimes the gift wrapping method. Its running time is proportional to the number of points times the size of the convex hull that you find. So it's not just input dependent, it's output dependent. So it's great if you only have a few points in a convex hull. And it's the analog of selection sort, basically. It generalizes to higher dimensions. Here we see a graphical depiction of how this gift wrapping method, the Jarvis March, works in 3D. Basically, it's still a line that rotates. You have a plane that rotates until it hits 2 points. Then you rotate it around that axis until it hits a third point, and now you have a face of this 3D polytope, which is the convex hull. And you keep doing that, discovering more and more faces of the convex hull. And when you're done, no more new faces to be discovered. Any questions about any of that? It's almost done there in 3D, and the convex hull forms, and all the interior points are excluded from the convex hull. Questions, comments? Yeah.
By rotating, you mean rotating around the edge, like until it finds another point?
Yeah, so you first touch it on some point, and then you rotate it until it hits the second point. And then you rotate it around these 2 points, because it's a plane now. And when you rotate around these 2 points, you'll finally hit a third point. So just like in 2D, a pair of points determines a line. In 3D, a triplet of points determine a plane. So you have to find this third point. Once you find this third point, you go off its edges, and you keep repeating for each of its edges. You rotate a plane planted there until it hits yet one more point, and you do it for the other edge, and so on, and you keep going until you exhaust all the edges, and there's no more new edges to be found. That's when you know you found the entire convex hull. Other questions? And it works in 4 dimensions, 5 dimensions. So planes, there'll be hyperplanes and higher dimensional faces and so on. But the generalization is pretty straightforward. Algorithmically, it's the same. And then we started talking about gram scan. I think that's where we stopped last time, right? So gram scan also finds a convex hull, but in a very different way. And again, this is from the same era, early 70s. Ron Graham, by the way, was the head of AT&T mathematical research for many years. He's now at UCSD, retired, I think, but great mathematician and algorithms designer. So you start with the point of the least x, and you sort all the other points by polar angle with respect to that point. So this line here, that's the least x coordinate point, vertical line, starts rotating, and as it rotates, it picks up the points in polar angle order, least to largest, right? So it's a kind of a linear scan. How does it know which points to pick? Well, it computes the polar angles of all the points, and then sorts those polar angles using any n log n algorithm like merge sort or heap sort or whatever. And as you scan around, you're forming this simple polygon, not necessarily convex. It's not the convex one, it just connects all the dots, but it connects them in polar angle order. Okay. And by the way, how do you compute these angles? You know, algorithmically in your program, you know, what kind of technique or approach would you use to compute these angles of all the points with respect to this anchor point? Any thoughts? Yeah, so you basically use trig, right? Use trigonometry, sine, cosine, you do the right things to get those angles. Right? So from a pair of segments, you can compute the angle between them if you take some sines and cosines. And never mind exactly all the details of that, but it's straightforward. How many have some idea what I'm talking about? Yeah, you just use trig basically. That's why we have you take trig and algebra before you get to sine. So we don't have to dive into all these gory details every time you mention it. Anyway, at the end you'll have this closed simple curve by virtue of it being sorted by polar angle around some origin, which is arbitrarily chosen as the least x point. And then comes the next phase, which is you start going around the periphery of this closed simple curve, which is not convex necessarily. But what you do is you turn it into an enclosing convex polygon by doing the following. You start, again, with the origin, which is the least x coordinate point on the far left. And then you keep scanning, and you get this next guy. And this could be a convex whole point. We don't know. We assume it is. And this could be convex whole point. We don't know. We assume it is. But we go to the next guy. And every time you go to the next point, you compute the interior angle that you're forming. Because you're sort of trying to wrap. It's almost like gift wrapping at this point. You're trying to wrap this point set. But this angle here will not be convex. It will be reflex. It will be greater than 180. And if that interior angle there is greater than 180, what do you know about this point there, right at the angle? Is it in the convex hole or not in the convex hole? Not. It can't be, because it's going the wrong way. The angle is bigger than 180. So what you do is you skip this point, and instead you connect straight there. You don't pass go, you don't collect $200, you go straight to the destination. And this angle now, the green one, is convex angle, less than 180. So then you pick the next one, and the angle there is okay. This angle is okay, so you keep going. And the convex hole could be all of these red lines, but now you pick the next one, and this interior angle here is bigger than 180. So you know that point cannot be part of the convex hole. So what you do is you bypass this point and go straight there. But notice what happened when you do that. This angle here became reflex, became bigger than 180. So you just keep regurgitating this heuristic, this rule, and since this is bigger than 180, you got to bypass this one again. So these two red lines become blue, and then this red line goes next to the next guy, and both of these points were eliminated from being inside the convex hole, for sure. Okay, and then you just keep going. You pick the next one after that, and the next one after that, and the next one after that. Oops, bigger than 180. So you eliminate this point and you go straight there. Okay. And these are now not part of the convex hole. But then when you go to the next one, you see this became bigger than 180. So you eliminate that one too, and you go straight there. And same thing happens here. So these angles that keep growing past one, it can cascade back arbitrarily far. How many can see that? It could be a cascade of them going backwards, not just the current one, and you keep going. But that's okay, that's what you do. So you eliminate this, and then these two are no longer being considered as part of the convex hole, and then you go straight there, and then straight there, that's okay. Oops, 180 again, bigger than 180. So you eliminate this guy, you go straight here, and then that's bigger than 180, so that gets eliminated, you go straight here instead. And then that's bigger than 180. You eliminate that, you go straight here, And so you're forming the convex hull in the red lines. And then you go here, and then here, bigger than 180, so you go straight there. And then when you go here, bigger than 180 right there, so you go straight here instead. And then you end up where you started, and that's where you stop. So you eliminated all these interior points using this method. How long does this scan take? Once you have the non-convex polygon, the simple polygons of the points, how long does it take to scan it this way, what we just did, in terms of the number of points and the number of points? How do you say n squared? How do you say better than n squared? How much better? How do you say n log n? So what is it better than n squared in this case? You're right, it is better than n squared. It's not completely obvious. How many see linear time for the scan? Okay, just a few people. Right? I want to make sure that most of the class sees this. Until then, we cannot go forward. Intuitively, you're right to suspect that it could be n squared. Why? Because you're going to go through every point, right? So that's n points right there you're going to go through. That's unavoidable. So at least linear. You can't not look at one point because that point could be very far away. And that would be part of the convex hull. If you skipped it, you'll never know, and you won't include it in the convex hull. That's a proof. It's got to be at least n. Every point's got to be inspected at least once. And this cascading, going back and going back, right? The cascades can go arbitrarily far backwards. How many can see that? So they can go n up to n backwards potentially. You could have picked 1,000 points, thinking they're part of the convex hull, but the 1,001st point, because he could have eliminated all these previous 1,000 points, one at a time going backwards. How many can see that can happen? Yeah, I mean, we already saw 3, 4, 5 points can cascade backwards. Arbitrary number can cascade backwards. So you're going through n points, and you can cascade backwards up to n points per point. So that's n times n, and there's your n squared. But that's pessimistic. Argue to me that it's linear overall.
You'll never hit any point more than twice, because if
Yeah.
you hit it twice, you know it's not part of the convex hull.
The force is strong in this one. So every point gets hit once on the way forward, and potentially once on the way backwards gets eliminated through some cascade. But once it does, it's never looked at again. How many can see that? Yeah. So each point can be looked at twice, once on the way forward and once on the way backwards to an elimination of a cascade. But that's it. So it's linear overall. The cascades can, a single cascade could go a lot backwards, but then future cascades cannot cover that same ground as that past cascade. You're done with that. Everything that was in the way of the past cascade going backwards will never be examined or gone over again. And that's the more insightful way to look at this process. So when you said n squared, you weren't wrong. It is big O of n squared, but it's also big O of n. And the two statements do not contradict each other. You never said it's omega of n squared. You never said it's theta of n squared. You said it's big O of n squared. Yeah. Just like you can say, you can buy a house for $1 billion. $1 billion is sufficient to buy a home. Not a false statement, but a very pessimistic, gross overestimation of the true cost. So, this is n squared, but it's also n. And we know it can't be better than n. So the scan part is optimal in terms of the number of points. How do you get it now? It's linear. Okay, any questions about that? So we just saw a form of what's called amortized analysis. Amortized analysis looks at an entire sequence of operations and calculates the cost for the entire sequence, not the cost for a single operation. And once you calculate the cost for the entire sequence, it could be a lot less than the cost maximum cost of a single operation multiplied by the number of operations n. And in real life, there's all sorts of examples like that too. Right? If you buy one plastic straw shipped from Amazon, it'll cost you probably $3.99. One plastic straw, because it'll be 1 penny for the straw and then $3.99 for the shipping, or $3.98 I guess for the shipping. But that doesn't mean if you buy 1,000 straws, it'll be $399, because the shipping cost gets distributed over the entire pack of straws. They don't weigh very much; they weigh just a few grams, right? So one straw will cost a penny. 1,000 of them will cost, $10 or whatever times a penny. 1,000 times a penny is $10 plus the shipping, just $3.99. So the price, the advertised price per straw, is a lot less than what it was before if you buy them in bulk. It's like retail versus wholesale prices. If you buy in bulk, you're saving the producer a lot of shipping and packing and handling and manpower, and, deliveries, and you get the discount. So here we get a discount for doing a lot of these, not just one cascade backwards, but all the sum of all the cascades add up to not very much, because you're doing a bunch of them and you're getting the wholesale bulk discount here. And in algorithm design, that happens a lot. It's called amortized analysis. And we'll get to more examples of that later in the course. It's a whole topic unto itself. Okay. How did we even get the blue polygon from the point set? Well, we sorted. We sorted the points, because the original point set was just points. There was no polygon involved. But we imposed a simple closed polygon on it. Simple means not self-intersecting. That simple doesn't mean trivial. It means non-self-intersecting. It's a mathematical term. So to get that polygon, we sorted. And once we sorted, we pulled off this so-called gram scan. And so the time to sort was really a bottleneck here in this algorithm overall for the convex hull. Once you sorted, the rest was linear time for the scan. The scan was the easy part, algorithmically speaking. Okay. So that was only linear time to scan, but n log n time to sort. And the worst case of this algorithm is also n log n time, because it's bottlenecked by the sorting, and the sorting works in worst case n log n if you choose the right sort. And by right sort, we mean merge sort, heap sort, any sort that works in n log n worst case. Just be careful not to choose a quadratic time sort like bubble sort or insertion sort, because then you'll blow up to quadratic time overall unnecessarily. You don't want to do that. And a drawback here is that this algorithm doesn't generalize to higher dimensions. Because how do you sort points in polar angle by, if you're in 3D or 5D? Not so easy, not so clear even how this kind of sorting is even defined in higher dimensions. It doesn't parallelize either, because the scanning is a linear kind of operation. So if you have multiple cores, it's not going to help you there, at least not in an obvious way. So that's gram scan. And it does intrinsically rely on sorting. Soon we'll see that sorting is sort of an essential part of convex hull construction. So that's not obvious at all now, at this point. We saw that sorting is sufficient to give you a convex hull with a simple scan step after the sorting. But we don't know that it's essential. You'll see that we can't get away from n log n. Convex hull is as bad as sorting. All right, so let's compare these two convex hull algorithms that we saw. The Jarvis's march, which is the gift wrapping method, that works in time n times h. And h is the size of the convex hull, number of points in the convex hull that you end up with. And separately, we saw that n log n gram scan, n log n times is sufficient to create the convex hull in this separate gram scan algorithm. And there's two algorithms, and they're incomparable, because I can ask you, which is better? Do you want to use this one, or do you want to use this one? Which is better than the other in terms of speed? Big O, asymptotic speed. Which one is better?
depends on the point set.
It depends on the point set. Sometimes this will be better, sometimes that will be better. When will one be better? If the size of the convex hull is less than the log of the number of points, then obviously this one will win. If it's a constant number or log, or the square root of the log, or something smaller than log, that'll be a better algorithm to use. On the other hand, if the size of the convex hull is almost all the points, if they all say lie on the periphery of a circle, all of them will be in the convex hull. And then n times h will be quadratic, because h is linear. And the time for running Jarvis's march is n times h. N times linear is quadratic, if h is as large as n. So in that case, n log n is better, and you use Graham's scan. But how would you know which one to use? I'll give you some arbitrary point set and say find me the convex hull, and you have both of these subroutines in your library already programmed, and they're both correct. Which one are you going to use? Ah, now you're getting it. You can use both of them, run both of them in parallel on two different threads. And whichever one finishes first, abort the other. And then you're guaranteed not to be worse than n log n, and often as good as n times h. And what are you paying for this? What penalty are you paying for this privilege? Space, a little bit of space, yeah. Not asymptotically, just maybe double the space, and what else? What are you paying in time? Yeah, roughly double, because you're running both. So you go back and forth, simultaneously running both. So you're paying double in time, and maybe double in space, even though you may be able to do it in place if you're clever enough. But the benefit you get is you don't need to know a priori which category your input falls into, and worry about falling into quadratic time, which will be terrible. So you can parallelize it. That's, again, meta-heuristic. And in real life, again, when you interview for jobs, you're using this kind of method. You interview for several jobs, not just one, and then make a decision. So that works. Notice that you don't even have to parallelize it. You can do it in serial. How would you do it in serial? There's the big hint right here. So just so you don't think you must run it in two parallel threads in a parallel fashion, you do it in serial. What you can do is you can run Jarvis's march first. For how long? Because you don't want to run it to the end, because you might end up quadratic time. That's terrible. Run it for n log n time on the clock. So you know what n is coming in the door. That's how many points you have. So compute n log n, run Jarvis's march for n log n time, and if it finishes, what do? Within n log n time? Or less. It can finish much quicker than n log n. If h is constant, it'll finish within linear time. But if it finishes within n log n time, you just report the answer. If you don't see it finishing within n log n time, what do you do then? Not a mystery at this point. Abort. Ignore it. So run the other one to completion. How many understand that Jedi trick? Okay. Any questions about that? So when I say meta-heuristic, run them in parallel, don't take it too literally. There's lots of ways to slice that idea into implementation. Right? Yeah.
So that's like a real life example, and we talked about n log n, we're like ignoring constants. So what if it was like 3n log n? And
excellent point.
Yeah.
So he's saying, how do you know the constant? Yeah, you compute n log n, but not just 1 times n log n. Maybe it's 2 times n log n, 3 times n log n. So what we do in practice, if you actually wanted to implement this serial meta-heuristic, you can profile things ahead of time, and every algorithm has some intrinsic constant that you can estimate by running it a lot of random point sets. So let's say your constant is 2.7. So let it run for 5n time, or make the constant 5. So 5n log n. just to be generous. So make it a little bit more than what you think the constant ought to be based on previous experiences and simulations and so on. Every algorithm that runs at a certain time, you can guesstimate an average what the constant is, or at least a range for the constant. We know between, say, 2 and 3. So let it run for 4 times n log n time, just to give it more and more slack. And if it still doesn't finish within that time, then abort and use the other one. Can you give me examples from real life when you actually do this? A meta-heuristic in a serial fashion, where if one doesn't pan out, you abort and let another one have a chance at it? Does that ring a bell as a general strategy for real life?
When maybe you're standing on a queue with a tourist and short and then you switch.
Yeah. So there's 2 lines at the market. You're standing in one line that you think will be faster. But after 10, 20 minutes, you see that it's not fast, and you switch to the other line, you give up. A more dramatic and probably more relevant example from real life for you is marriage. Just saying. This may have happened in your family. You may know people who actually did this heuristic. Give one person a chance and it doesn't work out, it's called divorce. And then another person may do better. Anyway, not to belabor the point, but this happens in real life all over the place. Right? You get in a traffic lane and you think it's a faster lane, all of a sudden you see it's not, then you abort that attempt and you switch over and you'll be better off. That's what we can do here. All right. Just can't say you didn't learn a lot about life in the class of algorithms. Now, you might ask, on average, what's the size of the convex hull? Because the runtime depends on the size of the convex hull. So you say, well, what is it in average? Well, that depends on the distribution. If your distribution is inside a square, random points inside a square, x and y selected independently, randomly, in a uniform distribution, say between 0 and 1, in a 1 by 1 square, the size of the convex hull will roughly be logarithmic in the number of points. So if you have 1,000 points inside a square, uniformly randomly distributed, the size of the convex hull will be log of 1,000, which is about 10. If you have 1,000,000 points, it will be about 20. So the convex hull is much smaller than the number of points, assuming it's in a square. If it's in an argon, a regular 4-gon or 5-gon, 5-gon is a pentagon, 6-gon is a hexagon. That depends on the number of sides. So it's R, the number of sides in the argon, times log n. So if it's in the hexagon, it'll be 6 times log n. And you can sort of see why. Because if you have a polygon of 50 sides, regular polygon of 50 sides, and you put 1,000 points in there, or even 100 points in there, when you compute the convex hull will sort of take the shape of the enclosing argon, 1,000-gon, or square, or hexagon. Convex will be so many points that some will be very close to the periphery, and when you take the convex hull, it'll look like the shape of the original polygon that enclosed it. How many can sort of intuitively see that? Yeah, that's what will tend to happen. So the size of the convex hull will have as many edges in it as the original gon that enclosed it. Whether it's a 50-gon or 1,000-gon or whatever. That's why you have this result. If it's in a circle, because about a circle is an infinity-gon, but the number of edges in the convex hull, if they're all in a circle, will not be infinity, obviously. But that runs as the cube root of that. So it's more than if it was in a discrete polygon, because it's a circle, because it will sort of resemble the circle. And in a sphere, it's a square root of that. So it'll be more of them. And so if you run Jarvis's march in a circle, the number of points in the convex hull will be roughly n to the 1/3, and the running time will be big O of n to the 4/3, because it's n times h, and h is n to the 3rd times another n, because that's the runtime of Jarvis. So it'll be n to the 4/3. It'll be worse than n log n if all the points are uniformly distributed in the unit circle. How do you understand all that? What is just a few of you? Any questions about this? I'm sort of now we're exploring these results of the size of the convex hull given that the distribution of the points comes from these particular scenarios. You can imagine other scenarios too. And by the way, how do we know these are the numbers? That's a lot of analysis. It's a lot of probabilistic arguments and analysis. And we're not giving a proof of these, we're just stating these results, just so we know, just so you know, these are not necessarily easy to derive, but that's what they are. Okay. Any other thoughts or issues about that? Okay. So let's explore a few more algorithms, just like we did for sorting. Let's explore a few more algorithms for convex hulls. So this one is will mimic quick hull, will mimic quick sort, and we call it quick hull, therefore. So here's how it works. You find the left and rightmost points with the largest and smallest x coordinates. So the first point is this, the second point is that. Right, so you bound it from the left and the right by vertical lines. So these are the two vertical lines here in green. And then what you do is you connect these two dots, the leftmost and the rightmost. And you partition around this line connecting these two dots in purple. So that partitions are set around the upper half and the lower half of the original point set. Remember, this is an analog of quicksort. So just like quicksort uses a pivot element, this is the pivot here in purple. And it partitions the rest of the point system into two subsets, one to the left and one to the right, just like we did in quicksort with numbers. Now, it's not necessarily a completely balanced partition, just like quicksort didn't necessarily guarantee a completely balanced partition of n over 2 and n over 2. It could have been 70-30 or 60-40 or even 90-10 or even worse. Same thing can happen here, but bear with me, let's see how it works first. So then you take a parallel line going up to the uppermost y coordinate of all the other points. In other words, you take the parallel line going up until it hits the farthest point away from this purple line. You do the same thing below. So you create these two green lines going parallel. Then you connect them into a parallelogram, 4 sides. Once you connect these 4 points in purple, what can you tell me about all the points inside this parallelogram versus points that are outside this parallelogram in these triangular regions around the parallelogram, around the quadrilateral, I guess. It's not strictly speaking of parallelogram, but a quadrilateral, a figure with 4 polygons with 4 sides. What can you tell me about all the points in the interior of this quadrilateral? Yeah?
They have to be inside the hole.
Yeah, they're going to be inside the hole and therefore not part of the convex hull boundary, right, that we're looking for. They're not laying on the convex hull itself. So we can eliminate all those right away from any further consideration. So with a simple linear time partition operation, we eliminated a large portion of the population of points that we at any further moment in time need to ever look at them during the execution of this algorithm. And that's a big win. Then what do? Then you run quick hull on what? Remember, it's like quick sort. So it's going to be recursive. It's divide and conquer. You're going to run quick hull on these regions here in these triangular portions outside this quadrilateral. You run quick hull here, you run it separately here, you run it separately there, and you run it separately there. So you run it 4 times. So quick sort runs 2 things recursively. This one runs 4 things recursively. I mean, after all, quick sort is in 1D and this is in 2D, so you expect more recursive steps perhaps, based on the convention. Once you find the convex hull of this, and the convex hull of that, the convex hull of this, the convex hull of that, you just merge. And by the way, when I say the convex hull of these points here, for example, I mean these red points here plus this purple point and this purple point. So the convex hull will roughly be this right here. And a line going like that. So the convex hull of each region will always consist of this long line between the purple points that are part of each set that we're recursing on. So these 2 purple points are part of this set. These 2 purple points are part of this set here. These 2 purple points are part of this set. And one of the lines of the convex hull will always be that long line here, then a bunch of other lines going around, whatever the convex hull is. Once you get these four convex hulls, how do you get the convex hull of the original point set? You just surgically splice them together. You splice this convex hull with this convex hull with this convex hull with this convex hull, ignoring this long line here, and you splice them using the purple dots as connectors. And then you'll have the convex hull of the original set if you merge and splice the four convex hulls of these four subsets. How many understand that? Okay. That was more than half a class. Good. Any questions about this? This will work. How fast will it work is the next question. And by the way, here's an animation of this is actually working. So the expected time will be n log n, by the same similar reasoning to quicksort. Right? On average, you eliminate a large portion, maybe a constant fraction, a half, maybe 3/4 of all the points, assuming they're kind of all over the place, and you converge and recurse on smaller and smaller point sets that diminish in size exponentially. So on average, you get n log n behavior, but the worst case is n squared, just like quicksort. How can it be n squared here? What would a worst case look like? Yeah, yes, my Padawan, the circle. So if all the points are on the periphery of a circle, and you do this trick, how many will be eliminated at every step? Almost none really. And you just keep recursing and recursing and recursing, and you're spending linear time to not eliminate anything. And but you're going to be recursing on smaller and smaller subsets, and eventually the job will get done. It's not going to be incorrect. It's just going to take quadratic time. Very little gets eliminated at every step. Now you get it. So quadratic worst case behavior, not so good. But it does generalize to higher dimensions. You can see how this will work in 3D. How many can sort of wrap your mind around what will this look like in 3 dimensions? Yeah, find the farthest and points on this side, draw a big plane. Once you draw this big plane, you can separate it into 2 subsets, and then find the other extremes, and you have some sort of a quadrilateral. You'll have some sort of a cuboid, something that looks like a skewed cube in 3D, and then you look at how many times do you recurse. 8, roughly. Not roughly, but exactly. And you just keep going, and this obviously generalizes to any dimension. And that's not a trivial statement, because some of the previous algorithms for convex hull did not generalize to higher dimensions, at least not in any obvious way. Like Graham's scan did not generalize in an obvious way to 3D or any other higher dimension. And it does parallelize. Again, some algorithms don't parallelize very well, and we already saw the Jarvis March didn't parallelize very well, but this one does, because you can recurse separately using separate threads in parallel on all these portions, just like quicksort parallelizes nicely in sort of merge sort. But insertion sort doesn't so much parallelize. But this one does parallelize, so that's an important property of it, even though it's worst case quadratic. All right, so just like merge sort, here comes merge hull. Any questions, by the way, on any of this? Quick hull and how it's an analog of quicksort with the same kind of algorithmic principle of operations as quicksort. Subdivide and conquer, recurse on smaller subsets. Do it randomly, so the split hopefully is more or less even or close to even. Keep going. Okay, so merge sort works a lot like merge hull works like merge sort. So how does it do it? Well, so partition the points arbitrarily into 2 equal subsets. Compute the convex hull of each subset separately, independently. So the original point set might be this, and I'm going to take all the blue points, put them in one set, all the red points, put them in another set, just randomly, I don't care how. Compute the convex hull of the red points, that's shown in red, the convex hull of the blue points, that's shown in blue, and now you gotta merge the two convex hulls together into a larger convex hull. If you can do that efficiently, you got yourself a merge hull algorithm that will work how fast? N log n. By exactly the same reasoning that merge sort works at N log n. That's an even split at every level. So the remaining question is, how do you merge these two resulting convex hulls? That's not completely obvious. And you gotta do it fast, and by fast, what do we mean here? How fast do you need to merge the two together for the whole thing to still work in N log n times? How much time do you have for the merge step? Better do it in linear time. You can't take too long for that, can't take N log n for that, otherwise the whole thing will work in N log n times log n, not N log n. So you can't take your time about the merge, it's gotta happen quickly in linear time. So how do you merge two convex hulls very quickly? So here's how you do it as a subroutine. You pick a point with the least x, and you form some angle monotone chain. So let's say here's a convex hull. I'm showing it to you kind of diagrammatically, as an ellipse. I mean, it's not an ellipse; it's a polygon. But it could have so many, could have a million lines in it, a million edges and vertices in it. But there's a convex hull, and if you take a point outside the convex hull and come up with the tangent lines to the convex hull, how do you pick a point outside the convex hull? Well, just find the least x coordinate in the entire convex hull or point set to begin with, and then subtract 10 from that, and then you get a point outside, for example. That's easy to do. Take that point outside and form supporting lines, tangent lines, like this. Find the line that's tangent to this convex hull. In a second, we'll see how fast you can do that. And find this other line that's tangent to the convex hull on the other side. And once you find these two tangents, you know that the polar angle sorted order of all these points in this chain here, all these points in this chain here, go from low angle to higher angle to higher angle to higher angle, all the way to the top angle of the top line. So all the angles there will go from low to high. And the outside chain, a similar phenomenon will occur. But let's just look at this chain, and it goes from low to high. The outside chain is the same thing. It goes from low, and if you keep creating lines here, it'll go higher and higher and higher polar angles until it reaches a maximum there. So if you think about these two chains from here to here on one side, and then from here to here on the other side as two monotone chains. Monotone means non-decreasing or non-increasing. It just keeps growing or just keeps shrinking. Monotonous, monotonicity. Monotone means going only up or only down. Doesn't do it repeatedly like a sine wave. How many understand that notion? You have two monotone chains of vertices by polar angle. It's monotone in the polar angle. Okay. So once you have this increasing angle going up from here to here, and from here to here as well, you can do something with that. You can use it to exploit that monotonicity to do something quickly, to do the merge quickly. We'll see how that works in a second. But for now, let's look at the following observation. So the convex hull of an L-gon plus an M-gon could have an L plus M total number of vertices. It could have all the original vertices in it. So for example, if I have a convex hull that looks like a square, quadrilateral, that's got 4 points in it, and another convex hull that looks like a pentagon, like a skewed pentagon with 5 points in it, the convex hull of their union could have a total of 9 points in it, but no more. How many can sort of see that? Yeah, it could happen. And let me show you an example where it does happen. Here's an L-gon, a polygon with L vertices and edges. And here is another polygon that's an M-gon, with M vertices and edges. And the convex hull of the union of the two of them could have as many vertices and edges as the sum of the two. And there it is in green. Every single vertex of the red and every single vertex of the blue will both all be in the convex hull of the union of the two. So, but it can't be obviously more than that, because that's all it is. But it could be as bad as that. So when you have these two chains, you can merge all of these points here and all of these points here. You can merge them into a single increasing polar angle order. How do you understand that? Let me say it in other words. If you have a sorted list and another sorted list, you can merge the two sorted lists into a single sorted list. How many can see that? And you can do it very quickly. How fast? Linear time. Linear in the sum of the two lengths of the two lists. Right? So you basically do this. And it doesn't have to be a perfect shuffle. It could be, it could be this, but that's okay. If one list is sorted, the other. That's why merge sort works so quickly. And that's why merge all works so quickly for the same reason. And you basically combine this list with this list into a single list that's monotone in the polar angle. Okay. And you do that for both convex hulls. So for example, one easy way to get a list in monotonic order, you start with this point, and then you go around this first convex hull in red, you go polar angle increases, 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 and then decreases, 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 and you combine these two chains into a single chain in monotonic polar order for the first convex hull, the first polygon in red. You do the same thing for the blue. Then you merge all the red and all the blue points in increasing polar order, monotone increasing polar order. And now you can do Gram scan on that list and get the convex hull of the union of the two polygons in how fast? How fast over time? Not a trick question. Remember, the Gram scan here works how fast in the total number of points. Just the scan part, not the sort. Linear time. How many get that? We went over that. Right? You even said it on the slide explicitly. Linear time to scan right here. So fast forward to the merge hole algorithm. Once we have the two convex hulls, for each one we take the two chains and merge them into a monotonic order, and then we take the two pairs of chains, merge into monotonic order, and merge those into yet another big monotonic order by polar angle. Now you can just do Gram scan on all these points, and in linear time derive the convex hull of both of them together. How do you get that? There's only a few people raising their hand, so ask me questions. I'll have to explain it a few more times. Yeah.
Can you explain it with an example?
Well, okay, so example would be like this here. So at this point, you can go into this convex hull and say that's the first point, that's the second point, that's the third point, and then the angle starts decreasing with respect to this anchor here, right? So right now we've been through this chain here on this side. So these 3 points here, 1, 2, 3, are this chain here in red. The other 2 points, or this one and this one, will be this chain here. So you take the 2 chains and you merge them by polar angle. So once you do that, you do that also for the other polygon, which is the other convex hull. You merge the 2 chains left and right by polar angle, and then you merge the 2 lists, the 2 combined lists, into polar angle, and now you have the entire point set made up of all of these red and blue convex hull points sorted in polar angle. And if you have a point set sorted in polar angle, gram scan can make a convex hull around very nicely in linear time, like we saw 2 slides ago. And that's what you do next. It'll give you the convex hull of the union of 2 original convex hulls. Why was it important to create this sorted list by polar angle in linear time and not just use merge sort or heap sort to sort them in n log n time, which would be even easier because then you don't have to worry about these chains and monotones and merging of things. And why don't we just use merge sort to sort all the points in polar angle and then do gram scan around? Let me ask you a leading question. Would it be incorrect to do that? Will it give you a wrong answer if you did that? When you say no, you'll still be right. Yeah, you'll still be right. It'll just be slower. Because you'll take n log n time just to do the merge step. But remember, this is a recursive algorithm. Merge sort. It keeps dividing the points into subsets and subsets, and just like merge sort. So let's go back to merge sort. In merge sort, what did you do? Divide the points into 2 equal size subsets, sort each one separately, and then combine them in linear time. How? By zipping together the two sorted lists into a single sorted list by a linear scan along the 2 lists simultaneously. How many remember that? That's how merge sort works. Good. How fast was this merge step? To merge a sorted list and another sorted list into a combined sorted list? Linear time. What if we took n log n time to do this merge step? Will it be incorrect? Will it give us an incorrect result if we took n log n time to do it? I'm going to say no, it'll still be correct. Yeah, it doesn't matter how long it takes you to merge the 2 lists into a sorted single list. But the longer you take, the longer the overall algorithm will take. If you do it n log n time just to do the merge, remember you do it recursively over and over and over again. It'll add up throughout the recursion steps, and the total time wouldn't be n log n. It'll be n log squared n, n log n times log n. Because it took too long to do the merge. So the whole point is doing the merge efficiently when you do divide and conquer. Divide and conquer, what's the general template? To solve the problem, you solve 2 sub-problems and then combine their solutions into the solution of the original problem. That's what divide and conquer means. But if you took too long to do this combination of the 2 sub-solutions into a larger solution for the original problem, the whole thing will run much slower if you took too long for the merge step, because it compounds on you. You're not just doing it once, this merge step, you do it many times throughout the recursion, up and down the recursion. So you have to do it efficiently. So here we have to combine the 2 convex hull solutions into a single convex hull efficiently, and that means linear time. Okay. So then, if you do it in linear time, you get overall n log n time complexity. And because the recurrence relation looks like this, right? The time to do n things is twice the time to do n over 2 things, plus this linear term. That's important. Right? The merge step, I'm color coding it in green here, is this term here in the recursion. And together you give you n log n time. And this generalizes to higher dimensions, obviously. And it does parallelize because you're solving the subproblems separately, independently, so you could parallelize them on different threads or different processors or different computers altogether. So, any questions about this? This is the analog for convex hulls of merge sorting numbers. At least conceptually, abstractly, it's the same template. And the same time complexity. And for the same reasons. Because it's a divide and conquer approach. Yeah.
So why does it generalize to higher dimensions? Because gram scan doesn't. So how do you sort those points?
Yeah, so when I say run gram scan, I kind of hard-coded it to 2D. That's a very good point. What I really should have said is okay, you have a point there.
does it actually generalize?
Yeah, so it's a question whether it actually generalizes. Because gram scan as it stands, as the way we describe it, doesn't generalize. All right, that's something I'll have to think about. But if you think about it before I do, or even if you think about it after I do, extra credit, because that's a very valid point. Excellent. Yeah.
Just to correct it, say for example, when we divide it, it's because both sides of it are kind of independent, and we divided the half of it. Like, say, in merge sort, if we divide it by two, we divide all of them into two sections again, and all of them are kind of independent. And if we parallelize it, finally we would get a linear time for sorting.
Yeah, but if once we go to 3D, it's not clear how gram scan generalizes to 3D.
I'm not asking about the three dimensions, I'm asking about the two.
Oh, the 2D, yeah, okay. What about the 2D again?
Because it's parallelizable, is it possible to say that you have linear time for this sort or even the merge sort?
Well, if you count the heavy parallelism, you could the overall clock time would be linear or less, maybe even less. Not sure if you can get a lot below linear, but if you write in a parallel fashion and you do all the right optimizations, you won't take n log n time, clock time. The total amount of work will still be n log n, but if you do things in parallel by deploying multiple processors, yeah, the time will be faster. It could be linear. The real question would be, could it be less than linear? And you could probably do it less than linear if you're very clever about the parallelization. You have to slightly modify the algorithm to get it below linear, sort of parallel. Okay. Let's talk about the lower bound for convex hull. So far, we came up with a bunch of algorithms that run in n log n time for convex hull. Merge hull, and gram scan, and some meta heuristics, they're all running n log n worst case. But what's the best case? We haven't said so far that it takes as much as n log n time in the worst case in general. Maybe there's an algorithm that runs in n log n time, or even linear time that works in general. We haven't shown that that's not true. We're about to show that that's not true. That the lower bound for convex hull is n log n, omega n log n necessarily, just like we argue that sorting takes n log n worst case time complexity. Right? And that was based on the decision tree model and the number of permutations that exists, and the log of that was n log n. Number of permutations was n factorial. Here the proof is maybe even simpler than that. Simpler than that of sorting. Because we're going to reduce sorting to convex hull. We can show here, on this slide, we will show that if you can compute convex hulls in general, you can sort in general. From the convex hull computation, you can extract a sorted order or an arbitrary plot set. And if once we show that, that establishes that convex hulls are at least as hard as sorting, because sorting is implicit in the convex hull computation. How are we going to do this whole order? Like this. Let's say you want to sort a bunch of numbers. So this is an instance of sorting. A bunch of random numbers on the number line. Arbitrary numbers. No assumption about what these numbers are. They're just arbitrary. N numbers on the number line. What we're going to do is raise them all to a parabola. So we're going to go to second dimension, because sorting is a one-dimensional instance. Sorting inherently is one-dimensional. How many understand that abstraction? Sorting is one-dimensional. It's just points on the x-axis, just numbers. Okay? Convex hulls is essentially a two-dimensional problem, or higher dimension. But the one-dimensional version of convex hull is trivial. So we're going to take these numbers that we're trying to sort. We're going to square them all. When you square things, you're creating a parabola, right? So once you square all these numbers, they'll end up on this parabola here very nicely. The parabola is y is equal to x squared. Right?
So by squaring them, creating the pairs x sub I, the numbers x sub I to be sorted, create the ordered pairs x sub I comma x sub I squared. So how many see the squaring these blue dots will raise them to the green parabola? Well, that's what happens. Right? Parabola is the equation y is equal to x squared. Once you raise them to the parabola, take your convex whole subroutine, however fast that runs. Let's say somebody magically provided to you a convex whole subroutine that runs in linear time. Never mind how, it's a black box, guaranteed to run in linear time, always correctly compute the convex whole. Take that black box subroutine, apply it to these green points on the parabola. What's the convex hull of these green points? What will the convex hull look like? All the green dots will be connected, and finally the two end dots will be connected to each other. So the convex hull will just connect all these dots using line segments. And finally, the last dot will be connected to the first dot. So in red here, we see what the convex hull of these green dots is going to be. The red segments. How many can see that? It's pretty unique. It has no choice but to be that. Why? Because it's not going to crisscross itself. Convex hull will be that necessarily. And this black box subroutine that you were magically provided that computes the convex hull of the green dot will return to you this red polygon. And remember, a polygon has to be given in order of the points around the periphery. So this black box subroutine that computes convex hull will give you this red polygon, and from the red polygon, you can march around the polygon in order, because you've given it in order, and from that polygon, you can infer and produce the sorted sequence of the original green dots, which is really the same order as the blue dots, for free. For free, we mean in linear time. From the red sequence of edges, you can produce the ordered sequence of blue dots, which is what you wanted to do to begin with, if you were to sort the blue dots. In other words, if I provide to you the red polygon for free, I just enabled you to sort for free. And by for free, I mean in linear time, for cheap. How many can see that? This argument is subtle. It's not long, it's just one slide, and 3 minutes of explanation. But it is subtle. So I'm going to repeat it. It's a lower bound argument. So it applies to which convex hull algorithm? All of them. Any of them. Any one of them now, or in the future, or ever, by us, or by some omniscient, omnipotent species that we don't even know exists. It applies to their algorithms too. In other words, no algorithm in the universe can ever find a convex hull faster than n log n time, faster than sorting. Why? Because if you're trying to sort something, you're trying to sort these numbers here, you can exploit convex hull subroutine into sorting for you for free. By for free, I mean linear time. So if you take an arbitrary black box subroutine for convex hull, we're going to trick it into sorting for us. How? By squaring all these points to be sorted. And by the way, if you have a bunch of points you need to sort, squaring them preserves their order in the sorted list. How many understand that? Squaring quantities preserves their relative ordering. If something is less than something else, their squares will have the same relationship. The square of the smaller one will be less than the square of the larger one. That's important. Squaring doesn't change, doesn't flip the order around, like some other operations will. Reciprocals do change the order, but not squaring. Okay, so square all the points. Create the green set from it. Once you square all the points, feed them to this convex hull subroutine, this magic convex hull subroutine that supposedly runs faster than n log n. And when it returns to you the convex hull of these points, which look like this, you can follow them in order around the periphery, the green dots, and that'll tell you what the order of the blue dots were in a sorted order, if they were sorted. We didn't sort them. We just fed their squares into a convex hull subroutine that gave us the convex hull, and from the convex hull for free, we found out what the sorted order is. And so if that subroutine works in linear time, we just sort it in linear time. How many can see that? So again, just a few hands are raised. I know it's subtle, so let's go over it a third and a fourth time until we nail it down, because this is an important argument. This argument will be repeated in other guises for many other problems for the rest of the semester. So better wrap your mind around it tightly now rather than later. It's a proof by contradiction. We're proving we're not a millionaire. That's hard to do. So when we do it, especially on one slide, that's a good day in algorithms. When you can prove a lower bound in a single slide. It rarely happens. But here it does. So again, what's the argument? We're reducing the problem of sorting to the problem of convex hull. It's a reduction. It's a transformation of one problem to another problem. We'll see many other transformations later in the course, especially when we talk about NP-completeness. So how do we reduce sorting to convex hull? Take an arbitrary set of numbers to sort. These are the x's, x sub i's. We're not going to sort them, but we want to sort them. We don't want to spend that log n time. But if we had a convex hull subroutine that sorts in linear time, that creates a convex hull in linear time, we're going to use it, exploit it, take advantage of it to sort for us in linear time as well, which we know can't happen. And therefore that subroutine, the convex hull, can't work in linear time either. In fact, it can't work in any time smaller than n log n. Because if it did, we would be sorting in that same time. But we notice the time for sorting is at least n log n, so a convex hull subroutine must require n log n time to do its convex hull computation, no matter what, no matter how clever it is. No matter how omniscient the being that designed it, it still must take n log n time. It cannot be creating convex hulls any faster than that. Why? Because if it did, we take an arbitrary sorting instance, raise it to the parabola, feed it to the convex hull subroutine, and from the red polygon that the convex hull subroutine returns to us, we are going to infer the sorted order trivially in linear time. And so the net effect is that we sorted in linear time with a single call to the convex hull subroutine. I'm going to get that. Okay, that's more hands. That's good. I'm glad I repeated it. And if you can sort in linear time with a single call to a convex hull subroutine, that's a contradiction. If the claim was that that convex hull subroutine works in less than linear time, or it works in less than n log n, or in particular in linear time, we know that's a contradiction because we can't sort in less than linear time. But with a single call to the convex hull subroutine, we sorted in less than linear time, the n log n time in particular in linear time. And that can't happen, so the convex hull subroutine, however long it takes to run, cannot run any faster than a sort algorithm. Because with a single call to a convex hull subroutine, we implemented a sort algorithm. With a single call to the convex hull subroutine. How? By taking the numbers to be sorted, not sorting them, instead raise them to the parabola, feed it to the convex hull subroutine, get the answer back, and from the answer, walk around the polygon and pick up the sorted order. And then you'll know the sorted order of the blue points, the original input, and then we sort it in linear time, if that thing ran in linear time. If it ran in any less than time than n log n, we would have sorted within that time, because the extra work we did, other than calling that subroutine, was linear amount of work. How many see that? We did a linear amount of work outside that subroutine call. Yeah. Is that clear? What was that linear amount of work? Just squaring all the numbers, feeding into that subroutine, taking the answer back, walking around the red polygon, that's the convex hull, and just reporting the sorted order of the points. Let me say one subtlety here. When you get back this red convex hull, you're not necessarily getting it this point first, lowest point first. You might get this point first, but then this second, third, fourth, fifth, sixth, 7, 8, 9, and 10. How many understand that? So what are you doing? How can in linear time can you still infer a sorted order if it doesn't return to you the least x first? Remember, it has to give it to you around in order of their occurrence around the polygon. Because if you don't give the polygon vertices in order, it's not even a unique polygon. You already gave examples last time where you can connect the dots lots and lots of different ways using a simple polygon. The answer is not unique. How many understand that? Remember that from last time. So convex hull subroutine must return the convex hull in order around the periphery of the convex hull, not just an arbitrary number of points. Right? But anyway, what if it doesn't give you the least x point first, but rather than one of the middle points first, and the rest in convex order, in increasing order, it goes higher, 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 and then low, and then higher, higher, higher again until it closes on itself. How do you infer the sorted order then? Not hard.
You can create maybe two arrays.
Yeah, create two arrays. One will be monotonically increasing, and the other will go back to the beginning, monotonically increasing again, and just concatenate them in the obvious fashion, and then you get the sorted order again. Or you can take the convex hull in red, figure out what the point is on the convex hull that has the least x, start at that point, and then keep going up all the way out to the end to the highest x coordinate. And then you'll have a sorted order there again. Okay, so what have we done? We've reduced the problem of sorting to the problem of finding the convex hull, and we did this reduction in linear time with a single call to the convex hull subroutine, whatever that was. We're not even saying how the convex hull subroutine works. It's a black box designed by omniscient entity, very, very clever. But what we're showing here is it can't be done, however clever it is, and we don't even know what's inside this subroutine. We just showed that it cannot work faster than the speed of a sorting algorithm. Because with a single call to that subroutine, we managed to sort arbitrary sets of numbers. How do you understand the logic here? That's still about a third to a half of the class. You want to ask me some questions about it? So I've repeated it about 5 times. That's okay. I'm willing to repeat it 5 more times, I guess next class, until it sinks in. Because it's a subtle argument. It's not a long argument, but it's a subtle argument. Ask me some questions. Yeah.
So one possible way to define convex hull is that it returns the unique polygon. Another way is it just returns a set of points that are
Yes,
in the convex hull.
and that's a great observation. He says to return the convex hull, you don't necessarily have to give it in order. You can just report which points are in or out of the convex hull.
So is it possible to do that second one in sub n log n?
No, it isn't. But that's a much harder proof than this. Yeah. So he's asking a very subtle question. He says, what if you just have to report which points are inside or outside the convex hull for a given point set? Just label the ones that are inside, not necessarily in any order. Because from those, you can sort of infer the order if you connect them in some increasing polar angle size. That's true. It turns out that even if you had to report which points are in the convex hull, not just give it to them in order, the n log n lower bound still holds for that scenario, but it's not this proof. It's a much harder proof than this. And you should probably at this point be glad we're not even presenting that proof here because it's a lot more complicated. And I can do one better even. Let's say you ask the simple binary question. I give you a bunch of points, and I ask you, are all the points that I gave you on the convex hull of this point set of all these points? Or some of them are not? Are any points in this point excluded from the convex hull at all? So now it's a binary question, yes and no. I'm not even asking you which points are on the convex hull. I'm just asking you, are all the points that I'm giving you on their own convex hull? Yes or no? That's still n log n, even for this binary query. And now the answer is just a single bit, yes or no. How do you understand that? That's even harder to prove than the first two. But that's also true. So this convex hull has a very non-trivial lower bound complexity to it of n log n, no matter how you ask it, with what variations, and even if you just ask the question, are all the points I'm giving you on their own convex hull, that's still n log n, it's just harder to prove. But there's something hard about that problem. By hard, I mean non-linear time. And it's kind of analogous to sorting. Sorting is actually easy. If I ask you the yes or no question about sorting, what will that question be? I give you a bunch of points, and what's the yes no Boolean predicate? Is this list sorted or not? That's sort of the analog of what we just talked about the convex hull. that question can be answered in linear time for sure. Go up to this, make sure it's monotonic, and then you'll know, sort of. In linear time, you'll know. But for convex hull, linear time won't even suffice to tell you if all the points are in the convex hull, or some of them are missing from the convex hull. So it's something about convex hull even a little harder than sorting, in the sense of this Boolean predicate. Bottom line is convex hull takes at least n log n comparisons no matter what. It's a proof by contradiction. It's also a linear time transformation of sorting to convex hulls. We'll see lots of other transformations. And, it'll be fun. Any other questions about this? So the first thing we're going to do next time is go over this proof again, much quicker, but this should sink in. And let me show you where, so in the book, in the Corman book, it's chapter 33, computational geometry. So look at this chapter. You'll see some of these insights about convex hull algorithms and so on. And in the other book, computational geometry by Perata and Shamus, and Michael Ian Shamus actually invented computational geometry back in the 1970s, using his PhD thesis as a jumping start to this whole field. It's chapter 3 and also chapter 4. You don't have to read this entire chapters, but it talks about Graham's scan and Jarvis March and time complexity. Very nice presentation. So how many have actually looked at this book already? A few people, okay. If you looked at it, I'm impressed. If you didn't look at it yet, I'm not sure what you're waiting for, but please do. Again, you don't have to read this chapters cover to cover, but just to reinforce everything we talked about in class and relevant problems from the homework or the problem sets and that kind of thing. Okay, any last minute questions or comments? All right, we'll see you next time.
You still get a sort of this by coloring the depth and have to go thick.
You could, or you could just surgically splice them without even doing drugs. This would be the all you gotta do is connect them right there and guarantee them. So you don't even have to rewrap them or re-wrap them. You could.
I didn't understand the splice.
Splice them this way.
If you're not listening,
Are we still looking at November in terms of early November?
We should nail down that. We'll nail down that.
okay, you sure?
But it's not gonna be very difficult, right? It's either gonna be late October or